In this section, we'll learn about the linked list data structure, which is a basic but very important data structure. And most of the questions in technical interviews are based on linked lists. So it is very important that you understand this concept properly and are able to write the code on your own. Okay, so now let's start. We have seen the list abstract data type in the previous section. It can be easily implemented using arrays. In Python, we have the list data type, which is an array-based sequence. So we can easily implement this list abstract data type using the Python list. Another way to implement this list abstract data type is by using linked list data structure. In a linked list, data is not stored in contiguous memory locations. This is an example of data stored in an array-based sequence, and this is an example of the same data stored in a linked list. This data is stored in contiguous memory locations, while this data is scattered here and there in memory. Here the list items are stored in sequential locations, so the relative positioning of list items is implicitly maintained. We know that this is the first item, this is second, and so on. In a linked list, the items are not stored in sequential locations, so the relative positioning of the list items is maintained with the help of links. A link is a reference to the next item of the list. So we have these links here. Each link refers to the next item. So with each list item, a reference to the next item is stored. Now the list item together with the link is called a node. So these all are nodes. These nodes are the basic building blocks of a linked list. The nodes are connected together by links and they collectively represent the linear order of the list. So this first node contains the first list item and reference to the second node. This node contains the second list item and reference to the third node, and so on. We just have to know where the first node is. All other nodes can be found by successively following the links. From first we can go to second, from second we can go to third, and so on. So while implementing a linked list, we maintain a reference to only first node of the list. And with the help of this reference only, we can access all the elements of the linked list. We'll call this reference start. So what is a linked list? It is a dynamic data structure that is made up of nodes arranged in sequential form. Dynamic data structure means that we can allocate the required memory while the program is running. A dynamic data structure can expand or shrink easily during runtime. So a linked list does not have a predetermined fixed size. It does not reserve any extra space in advance. It allocates memory for the next item as and when it needs it. In the case of array-based sequences, the size of the array might be more than the actual number of elements that are stored in it, resulting in wastage of space. Now for array-based sequences, we need large chunk of contiguous memory if many elements are to be stored. While in the case of linked list, there is a distributed representation of elements. Elements are not stored in contiguous locations. So many items can be easily stored even if contiguous memory is not available. And compared to arrays, insertion and deletion of elements is easier in linked list as there is no need to reallocate or reorganize the whole list structure. In arrays, insertion and deletion is expensive since it involves shifting of elements, while in linked lists, there is no physical movement of data while inserting or deleting elements. We can use linked lists to implement abstract data types like lists, stacks, or queues. Now let's see two disadvantages of linked lists. First one is that efficient random access is not possible. Means we cannot access elements of linked lists by using a numeric index. And the second one is that some extra memory is required for their implementation. This extra memory is due to the link that is stored with each item. Now these are the different variants of linked lists. In this course, we'll study about these 5 variants, out of which the single linked list is the simplest one. So we'll start with single linked lists. A single linked list is made up of nodes where each node has two parts, the info part and the link part. The info part contains the list item, the actual data that has to be stored in the list. And this link part is a reference to the next node of the list. This is an example of a single linked list with 6 nodes. The info part here contains an integer value. This can be of any other type also. We maintain a special reference variable that always refers to the first node of the list, and we have named it start. This reference is the identity of the list, and with the help of this reference only, we can access all the elements of the list. We have to use the link value from each node to go to the next node. We start at the first node and we can move from one node to the other by following each node's links. So if we just know this reference start, we can go to any node of the list. Now in Python, we have a special reference value called none. So if the link part of a node is none, it means there is no next node. No next node means end of the list. In this presentation, we'll denote a link that is referring to none by using this shaded box. So we use none to denote the end of the linked structure. This is the last node of this list, so its link part is none. For an empty linked list, the reference start will be none. Now let's see how we can implement a single linked list in Python. This is the class node that represents a node of a single linked list. This attribute info represents the actual data that has to be stored in the list. And this attribute link will refer to the next node. In this init method, info is initialized with this argument value and link is initialized to none. So whenever we create a new node instance, info will be initialized to the value that will be sent as argument and link will be none. Now this is our single linked list class. This attribute start refers to the first node of the linked list. So each single linked list instance will maintain a single reference to first node of the list. In this init method, we have initialized start to this special reference none. We can see that the list class itself does not contain any node objects. It only contains a single reference to first node of the list. In the next few lectures, we'll develop all the methods of this single linked list class. So right now you can make a new Python file and write this node class and single linked list class. As you proceed through the lectures, you can replace these past statements with the real code. So first we have this init method, then this method display list that will display the elements of the list. Then this method count nodes that will count the number of nodes in the list. This method will search for a value in the list. This method will insert a new node in the beginning of the list. And this will insert a new node at the end of the list. This one creates a list. Then this method will insert a new node after a given node. This method will insert a new node before a given node. And this one will insert a new node at a given position. This one will delete any given node. This one will delete the first node of the list. And this one will delete the last node of the list. This method will reverse the list. Now these two methods will sort the list using bubble sort. This one by exchanging data and this one by exchanging links. Now these methods are for inserting, detecting and removing cycle from a linked list. Then these two methods are for merging lists, and these methods are for sorting the list using merge sort. Now this is the end of the single linked list class. Now here we have created a new single linked list instance object. Currently there are no items in the list because in the constructor we have initialized start with none. Now with the help of this method create list, we'll create a single linked list, and then inside this while loop we'll perform various operations on the list with the help of all the methods of the single linked list class. Now in this while loop, first we are displaying all the options, and then depending on the choice entered, we call a particular method of the single linked list class. So if 1 is entered, we'll call this display list method. If 2 is entered, we'll call this count nodes method. So we have options till 18. In 19th option, we break the loop. So this is the code that tests all the methods of a single linked list class. In the next few lectures, we'll develop and test all these methods of this class. So before watching the next video, please make this Python file, and after every lecture, you'll be able to code 2 or 3 methods on your own. In this video, we'll see how to traverse a linked list. Traversal means visiting each node exactly once. So we'll start from the first node and visit each node till the last node. Before studying traversal, let us first see how we can move a reference forward in a linked list. Suppose we have this reference P that refers to this node. Now this is P link. It refers to this node. Now if we assign P link to P, then P will start referring to this node. So writing this statement P equal to P link makes P refer to the next node of the list. Or we can say that P has moved one node forward in the list. So this is the statement that we'll repeatedly use to traverse our list. Okay, now let's see how we can traverse our linked list. We have to start from the first node. So we'll take a reference P that refers to the first node. To make P refer to the first node, we initialize it with start because start refers to the first node. Now while visiting each node, we'll print the contents of the node. Now P refers to this node, P info is 10, so 10 will be printed. Next we write P equal to P link. So now P will refer to this node, and now when we print P info, 20 will be printed because info of this node is 20. Now again we write P equal to P link. P refers to this node now, and now P info is 30, so 30 will be printed. Again we write P equal to P link. P refers to this node. Now this time 40 will be printed. Again we write P equal to P link. P refers to this node. Now when we print P info, 50 will be printed. Again we write P equal to P link. Now this time P will become none. So we have reached the end of the list and we can stop. So we have traversed the whole list and printed the list items. We can see that we are repeating the same statements again and again. So we can write this in a loop, and the terminating condition for that loop would be when P becomes none. So this is the loop for traversing a linked list. We take a reference P and initialize it with start, and this loop continues till P is not none. When P becomes none, this loop will terminate. In each iteration, we are printing the value of P info and we are moving P forward by assigning P link to P. So this is how we can traverse a list starting from the first node till the last node. We can use the same loop to count the number of nodes in the list. Here we have taken this variable n and initialized it to 0, and whenever we visit a node, we increment the value of n. So when this loop terminates, the value of n will give us the number of nodes in the list. Similarly, we can use this loop to search for an element in the list. Now let us go to our program and see the methods for displaying a list, counting number of nodes, and searching for an element in the list. So we'll see the code for these three methods: display list, count nodes, and search. This method display list displays all the elements of the list. If a start is none, it means that the list is empty. In that case, we'll just print this message and return. Otherwise, we'll display all the elements of the list starting from the first element till the last element. We have already seen how this loop works. Now this method count nodes displays the number of nodes in the list. If you want, you can return the value of n from this method. Now this method search will return true if this element x is present in the list. Otherwise, it will return false. Let's see how this method works. We have taken this variable position and initialized it to 1. We'll increment it each time we visit a node. This reference p is initialized with start, and this is the same loop that we have seen in these two methods. So we are actually visiting each node starting from the first node. This is statement p equal to p link makes p move forward. Now whenever we visit a node, we check info of that node, and if info of that node is equal to x, then we return true from this method, indicating that x is present in the list. And before returning, we print this message that displays the position of x in the list. If p becomes none, it means that we have reached the end of the list and x was not found. So in that case, control will come here and we'll print this message and return false. Now let's see the method calls. We've called these three methods in options 1, 2, and 3. If we select option 1, list will be displayed. If we select option 2, number of nodes in the list will be displayed. And if we choose option 3, we can search for an element in the list. Now let's try to run this program. First we choose option 1. It is displaying that the list is empty. Next we choose option 2. It is displaying that number of nodes in the list is 0. Next we choose option 3. We search for an element. It is saying that 45 is not found in the list. Since our list is empty, whatever element we search, it will say that it is not found in the list. We choose option 19 and exit. Now here we had created a new single linked list instance, and in the init method we have initialized start to none. So the linked list that we have created here is actually empty. After that, we have called this method create list that will actually insert some nodes in the list, but we have not written the code for it yet. So that's why when we came here, the list was empty. In the next few videos, we'll see how to insert nodes in our list, and we'll see the code for this method create list. So right now your task is to write the code for these three methods: display list, count nodes, and search. So see you in the next video. Before studying insertion and deletion operations in a linked list, let's see how we can move in a linked list and find references to particular nodes. In this video, we'll see how to find reference to the last node of the list, reference to second last node of the list, reference to a node with particular info, reference to predecessor of a node with particular info, and reference to a node at a particular position. First, let's see how we can find reference to the last node of the list. This is the last node, so we need a reference to this node. This is the code that will give us a reference to last node of the list. We start at the first node by initializing this p with reference start. And this statement p equal to p link moves the reference p one node forward. While traversing the list, we had seen that the loop condition was p is not none. So there the loop stopped when p became none. Now here the loop condition is p link is not none. So here the loop stops when p link becomes none. And p link becomes none when p refers to the last node of the list. Link of last node is none. So when this loop stops, p will refer to the last node of the list. So this is how we can find reference to the last node of the list. Now let's see how we can find reference to the second last node of the list. This is the second last node. So we need a reference to this node. This is the code that will give us a reference to the second last node. Now here the loop condition is p link is not none. So this loop will terminate when p link becomes equal to none. And p link becomes equal to none when p will refer to the second last node of the list. Because when p refers to second last node, p link will refer to this last node and p link will be none. So when this loop stops, p will refer to the second last node of the list. Now we'll see how we can find reference to a node with particular info. Suppose we are given this value x and we have to find reference to a node that contains this value x. If the value of x is 30, then in this list, we have to find reference to this node. This is the code that will give us reference to the node that contains value x. This loop stops when p refers to the node that contains x. And if x is not present in the list, then p will become none. Now we'll see how we can find reference to predecessor of a node with particular info. Suppose we are given this value x and we have to find reference to predecessor of the node that contains x. If the value of x is 30, then in this list we have to find reference to this node, because this is the node that contains 30 and this is the predecessor of this node. This is the code that gives us reference to predecessor of the node that contains x. Now here inside this loop, we are checking p link info instead of p info. And the loop condition here is p link is not none. So this loop stops when p refers to the last node. Because when p refers to the last node, we do not want these statements to work. Now let's see how this code works. Initially, p refers to the first node of the list. Now p link is not equal to none. So we'll check p link info. P link info is 20. It is not equal to x. So this break is not executed and p is moved forward. Now again we check p link. P link is not none. Now we check p link info. P link info is 30. It is equal to x. So this break is executed and this loop terminates. So we can see that when this loop terminates, p refers to the node that is predecessor of the node that contains value x. Now let's see how we can find reference to a node at a particular position. These are the positions of the nodes in the list. Suppose we are given a value k and we have to find reference to a node that is at the kth position in the list. So if the value of k is 3, then in this list we have to find reference to this node. This is the code that will give us reference to the kth node of the list. Let's see how this code works. Initially, p refers to the first node and I is equal to 1. Now I is less than k and p is not none. So this p is moved forward and the value of I is incremented. Now again I is less than k and p is not none. So p is moved forward and the value of I is incremented. Now the value of I is not less than k. So this loop terminates. So we can see that when this loop terminates, T refers to the node that is at kth position in the list. This condition P is not none we have placed to terminate the loop in the case when there is no kth position in the list. That is, the number of nodes in the list is less than k. For example, if k is 10 and there are only 5 nodes in the list, then this condition P is not none will terminate the loop. In this video, we'll see how we can insert a new node in a single linked list. These are the different cases of insertion. We'll see all these cases one by one. To insert a new node, we'll allocate a node and make this reference temp refer to that node. Now this is the node class constructor. So this data will be used to initialize the info part and the link part will be initialized to null. Now first let's see how we can insert a new node at the beginning of the list. We allocate a new node and make this reference temp refer to this node. Now after insertion, this node will be the first node. So start should refer to this node and this node will become the second node. So link of this node should refer to this node. So first we make link of this node refer to this node. We write temp link equal to start because this node is referred to by start. Next we change start and make it refer to this node. So we write start equal to temp. So these are the two statements that we need to write for inserting a new node in the beginning of the list. The order of these two statements is important. Let's see what happens if we change their order. Now first we write start equal to temp. So start refers to this node. Now we can see that the link to this part of the list is broken. And now if we write temp link equal to start, this node will start referring to itself. And whenever we process the linked list, we'll be stuck in an infinite loop. So this is the correct way of inserting a new node in the beginning of the list. Now let's see how we can insert a new node in an empty list. For an empty list, start is none. We allocate this new node. Now this node will be the first node of the list. So start should refer to this node. So we just have to write start equal to temp and this new node will be inserted in the empty list. Now let's see how we can insert a new node at the end of the list. For this we need a reference to the last node of the list. We have already seen how we can find reference to the last node of the list. After finding this reference, we allocate this new node. Now link part of this node should refer to this node. So we write plink equal to temp. And so this new node will be inserted at the end of the list. Now let's see the code for all these insertions in our program. This is the method for inserting a new node in the beginning of the list. Here we are allocating a new node. Then we are writing these statements temp link equal to start and start equal to temp. This method will also work when we have to insert a new node in an empty list. Because for an empty list, start will be none. So we'll have temp link equal to none and start equal to temp. Now this is the method insert at end. We'll insert a new node at the end of the list. If the list is empty, we'll make start refer to the new node and we'll just return. Otherwise, we'll find reference to the last node of the list. Then we'll write plink equal to temp, where this p is a reference to the last node of the list. Now in this method create list, we'll create a new list. Here we are entering the number of nodes and here we are inserting all the nodes with the help of this method insert at end that we have just seen. Now let's come to the method calls. We've called this method create list here in the beginning and we have called these methods insert in beginning and insert at end in options 4 and 5. Now let's run this program. The create list method is being executed. So it is asking for number of nodes. Now we display the list. So we choose option 1. The list is being displayed. Now we'll insert a new node in the beginning of the list. So we'll choose this option 4. This new element was inserted in the beginning of the list. Now we'll insert a new node at the end of the list. So we'll choose option 5. So this new element was added at the end of the list. Now let's check our count nodes function. So the number of nodes in the list is equal to 7. Now let's search for an element in the list. For that we'll choose option 3. 45 is at position 1. Again we choose option 3 and search for 55. It is at position 7. Again we choose option 3. We search for 100. 100 is not found in the list. Choose option 19 and quit. Now we'll see how we can insert a new node between two nodes of a list. Suppose we have to insert a new node between these two nodes. For that we need a reference to this node. Now we allocate a new node. Now for this node to come in between these two nodes, the link part of this node should refer to this node and link part of this node should refer to this node. So first we'll make link part of this node refer to this node. We write temp link equal to plink. And then we'll make link part of this node refer to this node. So we'll write plink equal to temp. So these are the two statements that we need to write to insert this node in between these two nodes. Now the order of these two statements is important. Let's see what happens if we change their order. Suppose first we write plink equal to temp. We can see that the link to this part of the list is broken. And now if we write temp link equal to plink, then this node will start referring to itself. So this is the correct way to insert a new node in between two nodes of the list. Now we'll see how we can insert a new node after a given node, how we can insert a new node before a given node, and how we can insert a new node at a given position. These two statements of insertion will be same in all these three cases. The only difference will be in how we find this reference P. First, let's see how we can insert a new node after a given node. Suppose we are given a value x and we have to insert a new node after the node that contains x. If x is 56, then in this list we have to insert a new node after this node. That means we have to insert a new node between these two nodes. And for that, we need a reference to this node. We have already seen how we can find reference to a node that contains value x. After finding this reference, we will allocate a new node and insert it by writing these two statements of insertion. So this is how we can insert a new node after a given node. Now let's see how we can insert a new node before a given node. Suppose we are given this value x and we have to insert a new node before the node that contains x. If x is 45, then in this list we have to insert a new node before this node. That means we have to insert a new node between these two nodes. And for that we need a reference to this node. So if we have to insert a new node before a node that has value x, we need a reference to the predecessor of the node that contains x. We have already seen how we can find this reference. This code will give us a reference to the predecessor of the node that contains x. After finding this reference, we allocate a new node and insert it here by writing these two statements of insertion. So this is how we can insert a new node before a given node. Now let's see how we can insert a new node at a given position in the list. Suppose we are given a value k and we have to insert a new node at kth position in the list. If the value of k is 4, then in this list, we have to insert a new node here. The position of the new node will be 4, position of this node will become 5, and position of this node will become 6. So that means we have to insert a new node between these two nodes of the list. And for that, we require a reference to this node. So if we have to insert a new node at kth position in the list, we require reference to k minus 1th node of the list. We have already seen how we can find this reference. This code will give us reference to k minus 1th node of the list. After finding this reference, we allocate a new node and we insert it here by writing these two statements of insertion. So now this new node has become the 4th node, this node has become the 5th node, and this one has become the 6th node. Now let us see the methods insert after, insert before, and insert at position. This is the method insert after, that will insert a new node after the node that contains this value x. So here first we find reference to the node that contains x. After this loop terminates, if p is none, it means that x is not present in the list. Otherwise, p will refer to the node that contains x. And in that case, we allocate a new node and insert it by writing these two statements. Now this is the method insert before, that will insert a new node before the node that contains this value x. And we have seen that in this case, we need a reference to the predecessor of the node containing x. Now after finding this reference, we allocate a new node and insert it by writing these two statements. Before doing this, we have put these two checks. If the list is empty, start will be none, and in that case we'll just return, because in that case we don't want this statement to execute, because p will be none and accessing p link will give us error. Now if x is present in the first node, then we have to insert the new node in the beginning of the list, and in that case start has to be updated. So this case also we have handled separately. Now let's see this method insert at position. This method will insert a new node at the kth position in the list. And in this case, we have to find reference to k minus 1th node of the list. Now after finding this reference, we allocate a new node and insert it by writing these two statements. If the node has to be inserted at first position, in that case, we have to update the value of start. So this case we have handled separately. This is our initial list. Now we choose option 6. The new node was inserted after this node 4. Now we choose option 7. The new node was inserted before this node 3. Now we choose option 8. So the new node is inserted at position 3. Again we choose option 8. So it is showing that you can insert only up to position 10. In this video, we'll see how to delete a node from a single linked list. These are the different cases that we'll see: deletion of first node, deletion of the only node, deletion in between the list, and deletion at the end. First, let's see how we can delete the first node of the list. After deletion, this node will become the first node of the list. So start should refer to this node. So we'll just write start equal to start link. And now this node is not a part of the list. Now to delete the only node of the list, we'll just write start equal to none. And now this node will not be a part of the list and the list will become empty. Now let's see how we can delete a node that is in between the list nodes. Suppose we have to delete this node from the list. For that we need a reference to the predecessor node. So we need a reference to this node. Now for deletion of this node, link part of this node should refer to this node. So we'll just write plink equal to plink link. So this will refer to this node. And so now this node is not a part of the list. To delete the last node of the list, we need a reference to the second last node. After deletion, this node will become the last node. So its link should become none. We'll just write plink equal to none. So now this is the last node of the list and this node is not a part of the list. Now let's see these methods: delete node, delete first node and delete last node. Now this is the method delete first node that will delete the first node of the list. If the list is empty, then we'll just return. Otherwise, we'll make start refer to the second node of the list by writing this statement start equal to start link. Now this is the method delete last node that will delete the last node of the list. If the list is empty, then we'll just return. If the list has only one node, then we'll make start equal to none and return. Otherwise, we'll find reference to the second last node of the list. So after this loop terminates, P will refer to the second last node of the list and we'll write plink equal to none. And so last node of the list will be deleted. Now this is the method delete node that will delete a node that contains value x. If the list is empty, we'll just print this message and return. Now if x is present in the first node of the list, that means we have to delete the first node. So we'll do that by writing this statement start equal to start link and return. Otherwise, we'll find reference to the predecessor of the node that contains x. And then we'll delete that node by writing this statement plink equal to plink link. Now we have called these methods in cases 9, 10 and 11. Now let's run this program. So this is our initial list. Now we'll delete the first node of the list. So we choose option 9. The first node has been deleted. Now we choose option 10. The last node of the list has been deleted. Now we'll choose option 11. So now node with element 3 has been removed from the list. Again we choose option 11. We try to delete a node that is not present in the list. So it is showing that this element is not present in the list.